about 2 degree. So you can imagine in last 100 years we have 1.5 to 2 degree, and in next coming 10 years it can be again 1.5 to 2 degree. So how much it is fast warming in this earth. So there is a lot of policies all over the world, especially European Commission. They have said that plan about 2050, how can address these issues, particularly how can it reduce the CO2 emission. So they have planned in different way. One is a zero emission, and another is a negative emission. And in negative emission, there are few countries they have a good achievement, like in Sweden, Germany, because it was agreement on in France, one of the conference, which is also called the Paris Agreement, where they have agreed upon that all Europeans should go to the negative emission. But all over the world they have set a plan for the zero emission as well. So I'm not going into detail what is the negative emission and zero emission, but just you can imagine like in some mathematical calculation, mean if you are capturing and the emission is almost equal, then it is zero. So in this there are two parts which I am going to address today. One thing is about the existing system, meaning we cannot avoid the fossil fuels, because in every aspect for the power production we are using the fossil fuels. But it can be slowly, we can get rid of these fossil fuels, but it will take some time. So that's why first we have to address these fossil fuel based issues. So in fossil fuel based, there is a lot of industry. So actually from also last 100 years there is industry revolution, and industry revolution there is a lot of emission. So there is also one plan from the European Commission. I have recently completed one project regarding this climate change in Sweden. So they also set the target that they should address the existing industry, and there is a particular the power industry, where is the one is fuel reactor and other is the air reactor, and they have to introduce some oxygen carrying material which actually can separate inherently the CO2, meaning from CO2, CO, carbon monoxide to carbon dioxide. So actually in this they have a system, you can see from this fuel and air reactor, oxygen carrier can be introduced in the fuel reactor, where it can be reduced, and CO can get the oxygen, and it can be further separate the CO2, and it can be stored underground in a different way. Then further CO2 can be used for the different energy purpose. So here from this you can see like this way, in 2020 they have set some projects with the industry, but they have a plan till 2050, almost more than 3,000 projects they are going to install regarding this chemical looping system. So in this chemical looping system, what I am telling you, so this is the one of the technique where we can separate the CO2. And to prepare the oxygen carrying material, being a material scientist, so we are working on different oxygen carrying material, particular limonite material. Actually limonite is a natural ore, and it can be get from different natural resources. But problem is that in natural ores there is a lot of impurities, and those impurities can make some kind of problem in this chemical looping system, particularly in a fuel reactor. There is some kind of agglomeration. So after few hours it can be stop the overall system. So that's why there is need to prepare some kind of material where is some less impurity, but it should be more efficient. So that's why we prepared some synthetic limonite material, and that actually synthetic limonite is based on the iron and titanium oxide. Normally in natural ores limonite there is iron and titanium, but there are other some calcium and some other alkaline metals as well. But in this synthetic there is only iron and titanium base, but there are few ilmenite which is based on the iron manganese base as well. So like if we can explore here in Pakistan, might be it is the combination of iron or manganese or iron titanium. But this ilmenite is Egyptian and Canadian based material. So actually they have iron and manganese and iron and titanium. So further in different materials we have prepared to enhance further its performance and efficiency. We have introduced molybdenum as a catalyst in this material, which can enhance further its efficiency and performance. So I think from this morning, many people are tired here. So not going in more details. XRD is a very fundamental tool mostly students are using for this one. So just we have to confirm this XRD, what is the structure, what is the crystalline size, and what kind of phases we can achieve. Because I mentioned in ilmenite there are the different impurities, different phases. So just to confirm what we have prepared is a pure and how many phases are there. So, but there is another major tool in this chemical looping system to check the oxygen carrier capacity of any material. There is a TGA. I mean, normally it can be used for the thermal analysis at different temperature. So we have used TGA and different atmosphere like in redox cycle, oxidation and reduction. For reduction, we have used hydrogen, we have used methane, we have used syngas. So different fuel we have used, but also there is, because if in your power plant system you are using the coal, then you have to test also that material in a coal system. But the project was based on the biogas system. So how can we generate hydrogen from this biogas using this chemical looping system? So here you can see there are few cycles, and one is in fuel syngas and another is in methane. But in methane is a very stable redox cycle, but in syngas there is a different cycles. But in this syngas, the oxygen transfer capacity is much higher than the methane. But there is one formula how can we calculate the oxygen transfer capacity in the material. So again, you can find from the oxidation and reduction cycle. So in this further we have tested at different temperature, and then here you can see which material have a higher oxygen transfer capacity, particularly in syngas and in methane. Actually first one is the higher, but there is a problem, here is a pure iron base. But iron when Fe2O3, it reduces to Fe3O4, and it reduces to further FeO, and then it goes to the metal. So that's why it is not stable. But that's why here is titanium and manganese are using as a supporting material, and its phases can be stable in this way. So that's why here you can see there is a 50-50% ratio. Actually, this 50-50% ratio is also the available in the natural ilmenite material. So that's why in synthetic we have also adjusted 50-50%. So further to confirm its phases from the XPS, in which kind of phases are there, iron treatment, either it is oxidized phase or it's reducing phase. So further, and as I mentioned, we have introduced molybdenum as a catalyst to further enhance its oxygen transfer capacity and its performance. So in this, you can see again some TGA redox cycle are here, but here you can see is almost around in syngas more than 9%, but in methane more than 3%. But in previous it was around 2-3%. And normally natural resources they have actually 1 to 2% maximum. So that's why this synthetic material, of course, with the synthetic material, its prices will be high. So there is need further in how it can be, prices can be lower. That is another challenge. So future material actually focusing on different structural base like perovskite material, core shell, and there's a lot of techniques which you can play with the different materials, how it can be prepared and how it can be improved its performance. So just to give overview, one of my colleague, Dr. Zanfar already discussed about the fuel cell. As I mentioned earlier, Our focus, our research group, clean energy research group is focused on these clean energy devices which can address also climate issues in two parts. One, as I mentioned, based on the fossil fuels like in a chemical looping system, and others based on the fuel cell. So fuel cell hydrogen,